What is this summation notation? Instead of writing our series all out in number plus number plus number plus number plus number plus number, which can get really tedious, let's just try to compact everything and write it and express it this way. What this would mean is that let k be something called the summation index. That means k is going to be our counter. K equal to 1, k equal to 2, k equal to 3, so on and so forth. And let's once again reserve the alphabet n to represent the last ever number. So if we were to expand all of this out, we could actually write it as term 1 in mathematics. We have these things called operators. For lack of a better word, these operators legit just operate on your maths. In other words, they just do things to your maths. We're going to see many operators throughout this entire series, summation operator being one of them. Later on, we're going to see our differentiation operator, our integral operator, and many more. Let's talk about some of the properties of this so-called summation operator. The summation operator, if let's say C is just any number applied to this tk, which represents our terms, if we sum up all the constants which are being multiplied to the terms, it is the same thing as saying the constant is being multiplied to this entire sum. Because the counter k does not pertain to the number c, we can kind of extract out the c from this summation operator. The second property of this summation operator is that it is linear, in the sense that we can distribute this operator to these two terms. The first term being C1 times terms plus or minus C2 times terms, where C1 and C2 are not necessarily the same number. We can distribute this summation operator to these two terms, and once again, looking back at property number 1 of the summation operator, we can pull out the constants. Let's add up this series. The series is 1 times 2 plus 2 times 3 plus 3 times 4 and so on, okay? This series is neither arithmetic nor geometric, so we're going to have to learn some new ways to tackle series. Notice that each term of this series is given by each term of the series is given by k times k plus 1. When k equal to 1, we're going to get 1 times 2. When k equal to 2, we're going to get 2 times 3. When k equal to 3, we're going to get 3 times 4 and so on. Because we know that the summation operator is distributive, we've already uncovered this one at the very start of this discussion. The summation of the first n positive integers is simply just what about the sum of the first positive integers which are squared? Stated without proof, when are we going to see sums of powers ever again? We're going to see them when we do our statistics, when we start doing stuff like variance. Sum to n terms of the following series. For the first guy, let tk be any k kth term. So each term in this entire series given by 2k minus 1, 2k plus 3. But because we know that the sum of n terms is given by the summation of k equal to 1 to n of let's simply just expand this part out. But we know that the summation operator is linear in the sense that it can be distributed to every term, and every term we can factor out a constant. Simplifying all of this, the 3n comes from because we are adding 3 to 3 to 3 to 3 to 3 n number of times. Simplifying all of this even further, what we have here is that this entire series was broken up into these 3 smaller series called partial sums. The overall series can be obtained using the summation of each entire partial sum and then adding all of it back up to become n on 3 times 4n squared plus 12n minus 1. Unfortunately, the solution for part B is not the solution from part A just flipped upside down, even though part B is just every term of part A flipped upside down. Notice that each term for part B is let's break this fraction up into partial fractions. In partial fraction decomposition that we've done here, all we're doing is that we are splitting a denominator which has 2 factors in it into 2 different fractions, where a and b are just numbers. So a number on the first factor plus a number on the second factor. Now all we need to do is find numbers a's and b's for which these both fractions on the left and right side match up. Let's join them back up. If I were to take 2k plus 3 and multiply by the numerator and denominator of this first fraction, and I take 2k minus 1 and multiply the numerator and denominator of this second fraction, both sides' denominators will be the same. Hence, both sides' numerators must also be the same. All we need now is to find values of k which satisfy this equation. we're going to do something called equating coefficients. On the right hand side, on the left hand side, we only see a 1, we don't see a k. Hence, this part here must be 0. On the left hand side, we see a 1. On the right hand side, hence, this part here must be 1. Solving two equations with two unknowns, where the two unknowns are capital A and capital B. We're going to see that capital A is 1/4 and capital B is minus 1/4. Substituting our coefficients back into TK, we get that TK is equal to let's factor the 1/4 out. But because we know that our sum is going to be the summation of all the TKs, factoring out the constant and bringing the 1/4 to the left hand side. While we're at it, we might as well distribute the summation operator into these two terms. We now encounter a type of series we've never done before. This is neither, like I said, this is neither arithmetic nor geometric. It's just positive integer powers. What we're going to look at now is something called the method of differences to cancel everything off to get a final answer. Let's collapse all of this. How do we do so? Well, we know that k, regardless of either partial sum, k is equal to 1, k equal to 2, k equal to 3, and so on, all the way to k equal to n. Let's try numbers. K equal to 1. That being the case, let's try my k equal to 2. Let's try my k equal to 3. And so on, all the way to, let's try when k is equal to the second last term of this entire series, when k is equal to n minus 1. What would happen? And let's try k equal to n, the very final term. What do we have here? Do we notice something happening? We see that this 1 upon 5 and that 1 upon 5 cancel each other off. Have we gotten k equal to 4? We're going to see that this 1 upon 7 and the k equals to 4, 1 upon 7 will cancel off. Let me show you. Hence this 1 upon 7 from k equal to 2 and this 1 upon 7 from k equal to 4 cancel off. And so on and so forth. There are things always cancelling off. So the only surviving terms are this very first guy, 1, this second guy, this guy, and this guy. Our entire series of Sn equal to 1 over 1 times 5, 1 upon 3 times 7, 1 upon 5 times 9. All of this collapses down, which then collapses down to, we're only left with 1 upon 1 plus 1 upon 3 and minus 1 upon 2n plus 1 and minus 1 upon 2n plus 3. Simplifying all of this. And simplifying this further down, we're going to get this is known as the method of differences, because we really just put all the k values in to extract every term to hopefully have things cancel off. In this case, the 1 upon 5 and this 1 upon 5 cancelled off, 1 upon 7 and that 1 upon 7 cancelled off, and so on.